In this video, we work another example of an applied optimization problem. These are just word problems where we're using the first derivative test and second derivative test to answer their questions. And remember what optimization means. That just means we're finding minimums or maximums of some function as we're solving the problem. So the question says, a rectangle is bounded by the x-axis and the semicircle y equals the square root of 25 minus x squared. What length and width should the rectangle have so that its area is a maximum? So the first thing that I would do with this problem and any problem is sketch a picture if it's appropriate. And they're talking about rectangles, they're talking about semicircles, so sketching a picture is appropriate in this case. Now we're told that our rectangle is bounded by the x-axis. So I know that's going to be part of my bound. And we're told that it's also bounded by the semicircle, y equals the square root of 25 minus x squared. They told us it was a semicircle, so even if you didn't recognize that as a semicircle, you know it's supposed to be a semicircle. Now in order to make it look more like we're used to as far as equations of circles are concerned, I might take this equation and rewrite it in the standard form for the equation of a circle. So to get rid of the square root, I'll square both sides. Excuse me. So I have y squared equals 25 minus x squared. And remember with equations of circles, you're used to having x squared plus y squared on the same side. So we'll add x squared to both sides. And we get x squared plus y squared equals 25. Now if I compare that to the standard form of the equation of a circle, x naught, y naught, those are the numbers we're subtracting from the x and y. Well, we're not subtracting anything, so those are 0. Now, I guess I need to state this about the standard form of the equation of a circle. If my circle is written this way, the center is given by x naught, y naught. So that's the number that you're subtracting from the x and the y. So if I see a minus 1 here, that x naught is going to have the opposite sign. So if there was an x minus 1, I'd have a plus 1 here. So you identify the center that way. It's the numbers that you're subtracting from the x and the y, and the radius squared is on the right-hand side. So the radius is r. So comparing the circle that we have to this standard form over here, I see I'm not subtracting anything from the x or the y, so the center of this circle is just 0, 0. And the radius squared is 25, and r is a distance, so this is the positive, r is the positive square root of 25, which is 5. So I've got a circle centered at the origin with radius 5, and remember what we started with. We started with y equals the positive square root. Now if y is a positive square root, that means that y has to be greater than or equal to 0. So we don't get the whole circle centered at the origin of radius 5. We just get the part where y is positive or possibly 0. And the part where y is positive, that's the part of the semicircle, or that's a part of the circle that's above the x-axis. Okay. So I'm sketching a picture using equations of circles and what we know about equations of circles. And we're told we have a rectangle bounded by the x-axis and the semicircle. Rectangle. Well, that means the rectangle that we're talking about is inside the semicircle. So the rectangle looks like that. One bound is the x-axis, and that height or width, however you prefer to look at it, of the rectangle is given by the y value, a y value on that circle. The question says, what should the length and width of the rectangle be? Or what length and width should the rectangle have so that its area is a maximum? So the first thing we did was we sketched a picture. We've got our semicircle with the rectangle inside. Now we want to identify the function that we're optimizing. And in optimization literature, that's called the objective function. Okay, so I'm looking for the words maximum, minimum. A rectangle is bounded by the x-axis and a semicircle. What length and width should the rectangle have so that its area is a maximum? That's great. We're told we're going to maximize area. So area is our objective function. Now, in order to maximize it, we need to write area as a function of a single variable. So we need to write the objective function, which in this case represents area. Now, right now, it might not be a function of a single variable. Right now, area is just length times width, and that's my length, and this is my width. But I need to put those two pieces together. And I need to write this as a function of a single variable, not two variables, length and width, but a single variable. And I think because we're working in the xy plane, I think I'd like to write everything in terms of x. Now, because of symmetry, because we're dealing with a semicircle that's centered at the origin, this distance here and this distance here are the same. So if we go out to, say, x equals 4 over here, we're going to go out to x equals negative 4 over there. So if I treat x as a positive value, so I'm definitely on this side, then this length is x, and the length from there to there is 2 times x, because I'm going to double it. So length is 2x, and I'm choosing values for x that are positive, so I guess I should say that. And the width, well, the width is the y value on that graph. So right now I've got 2x times y, but I want y as a function of x when I'm on that graph. So I need some way to relate y back to x. This function that we're optimizing, I told you it's called the objective function. There are often other functions or other equations involved in optimization that will help you write your function as a function of the right number of variables. So we want this as a function of one variable. Those other equations are called constraint equations. So we want to identify any constraints, or in other words, like, how does y have to be related to x for this particular problem? Well, in general, y could be anything, but in this particular problem, y is a y value on this circle. And when we're on this circle, y is given by the square root of 25 minus x squared. So y equals the square root of 25 minus x squared is what we call a constraint equation. So I wrote over here, write the objective function as a function of a single variable. And I'll say you may need to use constraint equations. And a constraint equation is just an equation that relates the various variables over here to each other. an equation. I'll say describing the relationship between our independent variables. Well, what would have been an independent variable? Well, I'm going to put a little question mark by that. Like, they would have been independent, but actually they're dependent. Y depends on x. Okay. So we replace y with whatever it was in terms of x. Y is the square root of 25 minus x squared. And now my area function is a function of one variable only. Okay, so what did we do? We drew a picture. We identified the objective function. We're told to maximize area, so we know we're finding that. And then we had to write the objective function as a function of a single variable. I used my picture a lot. I said, well, I'm dealing with a rectangle, area of a rectangle is length times width. And then I said, okay, I'm in the xy plane. I'd like to write everything in terms of x or y. And so then we used symmetry to write the length as 2 times x and the width as y. Just by definition of y is that distance from the x-axis up. And then we said, but I want this as a function of one variable, not two. So I had to use this constraint equation to write it as a function of one variable, not two. Okay, now what do we do? Well, we were asked to maximize the area. And what else were we asked? We were asked for the length and width. What length and width should the rectangle have? So we're asked for 2 dimensions so that the area is at a maximum. So let's maximize the area function using either the first derivative test or second derivative test now, and then we'll go back and answer the question that they asked us. If you're wondering which one's easier, first derivative test or second derivative test, it really depends on you. First derivative test requires making that sign chart and thinking about where the first derivative changes signs. So if you've got to factor that first derivative generally, figure out where the first derivative is 0, which you had to do anyway, and then find the sign of the first derivative on all of those intervals. Maybe factoring is tough, and so you don't want to do that. In that case, I might go to the second derivative test. Just take the second derivative and plug in the critical values. Then you'll know whether the graph is concave up or concave down, and that will tell you whether you have a max or a min. Okay, so anytime we're maximizing anything, remember we always do this first. And I've got all these steps over here, but I want to go back over here. If I'm maximizing a function, what do I need to do? I need to find the critical points of A. And remember what critical points are. That means if our graph looks like this, those are places where the slope of the graph is 0. If the slope of the graph is 0, we might have a min or a max or a min or a flat spot like that. Critical points are also points where maybe the derivative is undefined. We might have a max or a min because the derivative is undefined. Okay, so we need to find the critical points, which requires that's the same as finding x values in the domain for which a prime equals 0 or a prime is undefined. Okay, that's just a reminder of what we're doing. Okay, so now we want to find the derivative of this. I see a product, probably going to use the product rule. And this expression can be rewritten. There's an implied 2 there and an implied 1 there. So this is 25 minus x squared to the 1/2 power. And now when we use the product rule, we have to use the chain rule for this piece. Okay, product rule says, take the derivative of the first function and you multiply it by the second function, undifferentiated. You leave it alone. And then you add the derivative of the second function times the first function. And you leave that function alone. Derivative of a constant times x is just our constant. And over here, got to use the chain rule. I've got an inside function. So let me write down what I did already. We've got 2 times 25 minus x squared to the 1/2 plus derivative of this piece. The derivative of a function to the 1/2 is 1/2 of the function to the 1/2 minus 1. That's negative 1/2. You put the inside function back inside, and then you multiply by the derivative of the inside by the chain rule. And don't forget that 2x from before. It's still there. I sort of run out of space. You're still multiplying all of that by 2x, because that was the derivative of the second times the first. The first is the 2x. Okay. Now we got our chain rule part. This part's done pretty much. Derivative of this part, derivative of 25 is 0. Derivative of negative x squared is negative 2x. So the 2's reduce there and there. And now we've got, this is a prime equals 2 times the quantity 25 minus x squared to the 1/2. I've got a negative 2x times an x is negative 2x squared times 25 minus x squared to the negative 1/2. Now that looks pretty bad. If I were to factor that, it would require some sort of fancy factoring with the negative 1/2 powers. I think at this point, I think I would rather use the second derivative test. But no, let's factor it to find the x values where the first derivative is 0. Okay. So before we do that, I would like to write this way. I've got, it should be a minus, looks funny, but it's a minus. 2 times the quantity 25 minus x squared to the 1/2. And over here I've got a 25 minus x squared to the negative 1/2, so that puts that in the denominator and makes that exponent positive. So this is a prime. Now, if I want a common denominator, I've got to imagine there's an implied 1 here. In order to make the denominators the same, I need to multiply this 1 by this denominator so that we get the same denominator. Now I can't just multiply the denominator by that. I have to do the same thing in the numerator and denominator so I don't change the value of my fraction. So this is 25 minus x squared to the 1/2 over 25 minus x squared to the 1/2. All of that minus 2x squared over 25 minus x squared to the 1/2. And now you've got a square root times a square root, even though it doesn't look like it. Remember, those are square roots. A square root times a square root is just the expression itself. Or you can think of it as a square root squared and you get the expression itself. So you have 2 times the quantity 25 minus x squared. Denominators are the same, so we'll subtract the numerators. Minus 2x squared all over this. And then if I distribute, 2 times the 25 gives me a 50. I'll have a negative 2x squared minus 2 more x squared. That's minus 4x squared all over 25 minus x squared to the 1/2. This is a prime. Okay, so we're getting there. That 50 and the 4x squared, oops, they have a 2 in common, so I can factor that out. Okay, now remember what we're doing. We're finding critical points. Excuse me. So we need to set a prime equal to 0, and we need to think about when a prime is undefined. Okay, so first we'll set it equal to 0. If I've got a fraction, it equals 0. Or if a fraction equals 0, the only way that happens is if the numerator is 0. Or if you want, you could multiply both sides by this denominator. You're still going to get the numerator equals 0 times the denominator, which is 0. The only way this happens is if one of these factors is 0. Obviously 2 is never 0, so we must have 25 minus 2x squared equals 0. Add the 2x squared to both sides. Divide both sides by 2. And then you're going to take the square root. Now, from an algebraic perspective, all we're doing, or I would need a plus or minus there. I get x equals plus or minus square root of 25, which is 5, over square root of 2. It's because the square root of a fraction is the square root of the numerator over the square root of the denominator. Now we said earlier something. We said if this is x, then the length is 2x. So we chose to make x be positive so that we could double it and get a length. So given that restriction, I don't need this negative 5 over root 2. I'll just keep the positive one. And the reason is because earlier we made that decision that x was going to be greater than 0. If x was negative, if x was allowed to be negative and the length was 2x, then I'd have a negative length, which doesn't make any sense. So we only want the positive one. Okay, so that is one of our critical values. It makes a prime equal to 0. Now, we also want to think about when a prime is undefined. A prime is undefined whenever that denominator is 0. Remember also that this is a square root. So let's look at a prime. And I'll write it with that square root this time. Okay. So we can't divide by 0. So clearly x cannot be positive or negative 5. Which, if you think about the problem itself, actually makes sense. Because if x was negative 5 or positive 5, that rectangle doesn't have any height. The area of the rectangle would be 0. But that's the maximum that x could be, would be negative 5 or 5. Like, I could let x equal negative 4.9. It would just be very, very short rectangle. But x could get to be all the way up here to the edge. It could get very close to 5 on this side, and then we double it to get the other side. But x can't actually be 5, because if x were 5, well, then we wouldn't have a rectangle at all. So keep that in mind. So a prime is undefined when the denominator is 0, and the denominator is 0 when x equals plus or minus 5. And of course, we've already chosen to require x to be positive, so negative 5 wasn't an option anyway. And this is also undefined whenever 25 minus x squared, that's the expression under this square root, is negative. And that's true whenever 25 is less than x squared. And I think this is an inequality that's easiest to solve graphically. Y equals x squared looks like this. Y equals 25 looks like that. If we're saying 25 is less than x squared, that's the same as x squared being greater than 25. If I want to solve this equation, or excuse me, that inequality graphically, I just look at when the parabola is above the line y equals 25, because it's greater than, it's above it. That happens over there and over there. You're saying, okay, what does that have to do with the domain? Well, the x values that go with those two little parts of our parabola are where this is undefined. So when x is greater than 5, or when x is less than negative 5, yeah, we're going to be in trouble. You may have forgotten this, and that would be totally okay and expected. Another shorthand way to say that is that the absolute value of x is greater than 5. And we also have problems when x is positive or negative 5, so we could use greater than or equal to 5 there. So I guess we could have used these signs the whole time. Okay, so this is undefined here, but we kind of knew that anyway because this y equals the square root of 25 minus x squared was only defined between negative 5 and 5. So yeah, a prime is undefined there, but those values weren't in the domain anyway. So we set a prime equal to 0. We solved for x. You always want to consider x values that cause a prime to be undefined. We did, and none of them were in our domain anyway. So I guess we should have talked about domain. Let's think about the domain of A, and the realistic domain, I'll call it, for this problem. Now, A as a function of x was 2 times x times the square root of 25 minus x squared. The domain of this is the set of all x values such that this expression under the radical is positive and that's positive when it's not negative. So I guess what I'm saying is this is when it's undefined. It's going to be well defined between negative 5 and 5. So the domain of this is negative 5 to 5. It's the same as the domain of that positive square root of 25 minus x squared. It's the domain of the equation of the semicircle. Okay, but this is not the domain for our problem. We said earlier when we set this problem up that the length was 2x and x had to be greater than 0 so that the length was actually positive. So that means this is the domain of this function, but the realistic domain for our problem is this. X has to be greater than 0 and it should be less than 5. And I think that makes sense because x has to be positive, and then it has to be strictly less than 5 because if x were equal to 5, there would not be a rectangle at all. So this is our realistic domain, or if you prefer, you can use interval notation, 0 to 5. Okay, so we found our realistic domain for this problem, and we had a critical point earlier. It was 5 over square root of 2. Now we want to determine if that critical point corresponds to a minimum or a maximum. I think this time, would I rather take the second derivative and substitute or make a sign chart for that first derivative? Now let's make a sign chart for the first derivative. Let's do first derivative test. Either test will work. If you prefer the second derivative test, you can do that. Just remember how it works. You take the second derivative, you plug in the critical point, find out if your graph is concave upward or concave downward there, and that'll tell you whether you're at a min or a max. Okay, so A prime was 2 times the quantity 25 minus 2x squared. And then we've got 25 minus x squared to the 1/2 in the denominator. So when I make my sign chart for A prime, well, normally I would go from negative infinity to infinity, but now I'm just going to go from 0 to 5 because of that domain, the realistic domain for our problem. And I'll write my critical value on here. It's 5 over square root of 2. And I'm using my calculator to get a numerical approximation. And isn't that a nice calculator that always gives you the exact answer? Press the SD button if you're using the Casio. So we had about 3.54. So A prime is 2 times 25 minus 2x squared divided by the square root of 25 minus x squared. Now on the interval from 0 to 5, well, on any interval where this is well defined, this positive square root is going to be positive, except for when it's 0. And it's not 0 on either of these intervals. It's only 0 at x equals 5 and negative 5. Okay, now we just need to determine the sign of this guy on these two intervals. You can pick any test value you want. Since this is 3.54 approximately, I might pick x equals 1 over here and x equals 4 over there. If x is 1, we've got 25 minus 2, that's 23. And 23 times 2, definitely positive. So I've got a positive divided by a positive, which is positive. Over here at x equals 4. 4 squared is 16. 16 times 2 is 32. 25 minus 32, definitely negative. Or yeah, 25 minus 32, yes, I said it right. It's definitely negative. Multiply it by 2, still negative. So I've got a negative over a positive. It's whoops, I said negative and I wrote positive. Okay, we're there. What does that mean? Remember, if the first derivative is positive, that means the original function is increasing. First derivative is positive, that means the graph has positive slope. So we've got positive slope over here on this interval. And then over here, the first derivative is negative, so that means the graph has negative slope at all of those x values, so it's going down in general, it's decreasing. And remember, it had 0 slope here, so the function went from increasing to having a 0 slope to decreasing. We must have a relative max there. So we'll say, create a sign chart, find any relative extrema using the first derivative test. Or if you take the second derivative and plug this in, the graph should look like this there. The graph should be concave down. So if you take the second derivative and plug in this value, your second derivative should be negative, and so you'll know you have a relative max. So that means a of 5 over root 2, whatever that value is a relative max. And because the function looks like this on this interval, it's going to be an absolute max because it goes from increasing to decreasing, and it's not defined at 0 or 5. Yeah, we're going to have a relative max, or an absolute max there. Now let's go back and make sure we answered the question. Question said, what length and width should the rectangle have so that its area is a maximum? The length was right here. Remember that length was 2x. And the width was the y value on the graph, but remember the y value was given by the positive square root of 25 minus x squared. So let's calculate the quantities that they asked us for. Excuse me. So length was 2x, and x was 5 over square root of 2. So we get 10 over root 2, or if you prefer, you can rationalize. You don't have to, though. Something that people used to do because they had charts of irrational numbers to refer to, but now we've got calculators that can do that for us. It's not necessary to rationalize, but it turns out to be 5 times the square root of 2. And the width was the y value on the graph, and the y values were given by the equation of that semicircle. So I've got 25 minus 25 over 2. So I got 1/25 minus a half of 25. So I think that's going to be half of 25 over 2. And make sure you take the square root. And you can rationalize if you prefer. You don't have to. Okay, so always make sure you answer the original question. So the original question was, what length and width should the rectangle have so that the area is a maximum? Yes, we'll say the area is maximized when the length is 5 times the square root of 2 and the width is 5 times the square root of 2 over 2. And let's approximate those numerically and then graph it just to visualize what we've done. 5 times the square root of 2 is approximately 7.07. And 5 times the square root of 2, divided by 2 is approximately 3.54. Okay, so what does that mean? I didn't do a very good job with my grid. That's okay. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Just trying to do a better job with this picture, but accuracy is important when you're trying to visualize what it is you're doing, but I'm having a little bit of trouble today. It's a little crooked, so I'll just turn my piece of paper like this. Hopefully you guys don't mind. Okay, so this length is 5 times the square root of 2, which is 7.07, but we're splitting that, like half of it is over here and half of that is over here. I'm sorry my picture is so bad. It's okay. Half of that turns out to be 3.54. So if this is 3.5, so we're going out to 3.5 in both directions. It's just so bad. It's such a bad picture. Maybe I'll go over here. I've got another piece of space. Okay, so we go out to about 3.5 for x in both directions. I'm trying to draw a rectangle. It's not perfect. It's okay. Okay, so that's the rectangle of maximum area. This is 5 root 2 over 2. So the length is what we get when we double that. And this is 5 root 2 over 2. And this is about 3.54. And then this is twice that over here. If you're saying to yourself, isn't that exactly the same picture that we started with? Well, yeah. But think about the other x values. If x is, let's say, 1, then our rectangle would look like this. So we could still inscribe a rectangle in the semicircle, but that area, it's not going to be as large as this area. Or you could choose a different value for x. Maybe x goes from, let's say, just -3 to 3, which is a little closer. So we look at that area. Apparently that green area is less than the area of that red rectangle. What if you're saying, well, what if we go out farther? Let's make it short and wide. Maybe that's our rectangle. All of those are rectangles that are inscribed in this semicircle, but the one with the maximum area is the red one, the one that I started with at the beginning. The maximum area is 5 times the square root of 2 over 2. That's our width, width, times 5 times the square root of 2. That's the length. If we multiply those together, we get the area at a maximum. We could find lots of other areas, but none of those, or we can find lots of other rectangles, and all those rectangles will have other areas, but the maximum area occurs at that point. And how do we know? Because calculus told us, because we know how to optimize functions using the first derivative test or the second derivative test, and because we set it up correctly to begin with. So that's an example, another example of applied optimization. Just going to go through the steps with you one more time before you get started on your practice problems. Okay, you read the problem statement. If appropriate, you want to sketch a picture. I almost always sketch the picture. You might have to look up some old things, like the equation of a circle from pre-calculus. Look it up if you need to, but sketch your picture. Then you want to identify the objective function. They're going to tell you what the objective function is in the problem statement somewhere, somehow. They're going to say maximize this or minimize this. And you're going to say to yourself, what is it that they want me to maximize? Read carefully. You say, the area. That's my objective function. So then you need to write your objective function in terms of one variable only. Initially, it might be in terms of 2 variables, like ours was. Now, if it happens to be in terms of more than one variable, then you need to write all of the variables here in terms of a single variable using some other facts from the problem. Those other facts are usually in the form of equations, which we call constraint equations. This is a constraint equation right here. So I replace y with this constraint equation. Y is this in terms of x when I'm on the circle, and now I've got my area as a function of a single variable. So I can use the first derivative test or second derivative test from Calculus 1 to optimize it. So, okay, so now we're going to do one of those tests. We start both of those tests with the same procedure. We need to find the critical points of our function. And remember, critical points are points where the derivative is 0. So you might be at a min or a max, or you might just be at a flat spot, or points where the derivative is undefined. You need to find those. We don't know what the graph looks like, but in order to find these, algebraically, we do this. So we compute the derivative, we set it equal to 0, which might involve some algebra, getting a common denominator, and all that jazz. Eventually, you set it equal to 0, and you solve for x. Then you only keep the x values that make sense in your problem. We made an initial assumption that x was going to be positive, so that our length would we could represent our length as 2x. So I just kept the positive x value because of my assumption from earlier. Then I thought about the places where a prime was undefined, and it was a really good, it was good practice for us in thinking through when this function is undefined. But it just so happened to tell us nothing new. It said a prime is undefined when we're basically outside of the domain of this function, except for at the endpoints of that function. So the domain of this function was -5 to 5. A prime is undefined outside of this interval and at -5 and 5. So then we said, okay, this is my domain, and now we need a realistic domain. We said x had to be positive because it's a length, and x has to be less than 5 because it's a distance inscribed in the semicircle. So that's our realistic domain. We use the first derivative test on the realistic domain to determine that we've got a maximum here. So we made our sign chart, figured out where we have a maximum, and most of the time I would go ahead and find the maximum. Somebody asks me to maximize the function, I'm going to give you the maximum. But this time I didn't, because I wasn't asked for the maximum area. What was I asked? I was asked for the length and width the rectangle should have so that the area is at a maximum. So once we had this, well, you can't find it now. I don't know how I lost it. But once we realized that we were at a maximum, then we went and we found the length and width that would optimize our function. And the length happened to be 2x. So we multiplied that critical value by 2. And the width happened to be y. So we substituted the critical value in here to find the y value. And those were the dimensions that gave us the maximum area for that rectangle. And then we talked about why that's true by drawing all these pictures of different rectangles of different areas and saying, the red one, that's the one. That's the one we're looking for. That's the maximum area out of all those possible rectangles that we could inscribe in that semicircle.